Hey everybody, and welcome back to Algebra 2 Online. So the plan for today is to just do a few problems to kind of help you get ready for the upcoming quiz. And these will just be a bunch of random different kind of log exponential type problems. Probably one of the most important things that we've done so far is just talk about how these logs have domain issues. So it all roots from the fact that, with exponential functions, they have restricted ranges, right? They have like a cutoff right here. And so log functions are going to get a cutoff in, the y-axis. And so, most log functions kind of look like that. That would be like log growth, but you can absolutely have like log functions that come down like that. But that idea is really important because it ties into solving log equations and inequalities and all this sort of stuff like that. So you need to know how to find the domain of them. And so this is a rational function with a log in it. And so it's going to have actually like two domain issues. Okay, so maybe we'll split it. You can definitely divide by 0, right, which would be bad. So we don't want to do that. So we want log base 2 of x squared to not be equal to 0. So if we raise both sides, exponentiate them is actually the term. So we make these exponents is the idea. Then we use base 2 exponential because that'll cancel here, right? So then we can go and say, okay, now x squared just can't equal 1, right? And so x just can't be plus or minus 1, right? So that's this part done. And then we also have a log. And so we're going to have to deal with the inside of the log. So we know that for log functions, the inside just needs to be greater than 0. I think this was actually even in our last video. If you have an x squared like that, right? This thing is almost always greater than 0, except right at the origin right there. So basically all reals but 0 work there, right? So what we get is, as a final answer, we're going to get all reals, but x just can't be 1, -1, or 0, right? And you can actually see it. This is the actual graph of it. I didn't do a great job showing it. So that's the 1 and the -1. And then it's really, really hard to see, but the graph is actually curving like in at the last second, kind of like that. And I think I'm going to erase that. But it basically is acting as another asymptote right in there at x equals 0, the y-axis. So, so that's how we can find the domain of that one. All right, so another really important thing that we did is just graphing logs and exponentials. So let's maybe do this one in red or something. So there's a lot of transformations going on here. You've got, like, just to kind of go through them, you got a 2 right in there, right, which is a horizontal compression by a factor of 2. You've got a 3 on the outside, which is a vertical stretch by a factor of 3. A vertical flip, and then this is a shift down 3, okay? So with these ones, I'm always looking for 3 things, all right? I want basically a 1 point, which is not too much to ask, 1 point, a horizontal or vertical asymptote, and that just depends on which function you're graphing, the log or exponential. And then I just want general shape. So you need to know whether the thing is growing or decaying, that kind of thing. So, in this one, it's a base 3. And so if the base is bigger than, maybe I'll just write it down here again. If the base is bigger than 1, that's how you can grow. And then if the base is between 0 and 1, it's like a fraction like that, that's the cases where it's going to decay. And the good thing is that's true for both exponentials and logs. So this one is base e, right? So it's going to grow. This was base 3, so it's going to grow. So that's kind of nice. And I do think the easiest way to do this is to just go point by point. So, for exponentials, we start right there at 0, 1. And then if there's horizontal compression by a factor of 2, that's just not going to move, right? It's going to stay there, right? Then you can scale it by a factor of 3 vertically, so that would move it, right, up there. Then the negative in the very front happens, and we flip it down to negative 6, right? And then we I'm sorry, I multiplied my numbers wrong. This is 6, but we multiplied this by 3. I don't know how I got to 6. Anyways, this should be different. So from here, 2 does nothing. Multiply by 3, and you're definitely at 3, not 6. Then the flip happens. You're down here, negative 3. And then the shift down 3 happens. So now you're at negative 6. So that is where the point is, right? It just went 0, 1, 0, 3, 0, negative 3, 0, negative 6. Okay? And, we've seen this before, but with exponentials, this number at the end, it will always tell you where the horizontal asymptote is. This number inside will always tell you the left or right shift. So that one tells you where the vertical asymptote is, right? So I can also just plot that negative 3 horizontal asymptote right at the beginning if I wanted to. It's fine. The reason that is tied to the horizontal asymptote is it's normally at 0, right? So whatever this number is will represent the vertical shift. So it'll represent where that horizontal line goes, right? So then we just have to think, we've got our point, we've got our line, general shape now. So we were growth, right? But we flipped down, and so it'll look sort of like that, right? That's what the exponential would look like, okay? All right, so on to the log. So here we just have 3 transformations. Shift to the right 1, vertical stretch by 2, and a vertical flip, okay? So with these ones, I always start at 1, 0, right? This one shifts 1 to the right, so now we're at 2, 0. Then you do vertical stretch, but you're multiplying 0 by 2, so it's just going to stay here, right? And then there's a flip happening, but you're on the line of reflection, so that also won't go anywhere. So actually, that is my point for the log, all right? And then the asymptote, right, was here, but I shifted it over 1, and so it's right there now at 1. This is x equals 1. And this asymptote was y equals, y equals, what was it, minus 3. And then you just need general shape. So it's log growth, okay? But there is a negative, right? So it would have been something like that, right? That's kind of what log growth would look like. But then we flip it. So it's going to look like this. So you've kind of turned it into sort of log decay, right? So it's just going to do something kind of like that. And that's it. Just 1 point, dotted line, general shape. That's all I'm looking for. All right. Another important thing in this unit so far is just evaluating logs without a calculator. So all of these here are ones that are actually pretty nice, and you should be able to do them without a calculator. So it's just really for time reasons. Like, I wouldn't want anyone going and being an engineer or something like that and running into stuff like this and taking out a calculator to simplify them, because they really are, once you do enough of them, it's really, to me, it looks the same as doing like 2 plus 3. It really is that kind of straightforward, that I don't want you overthinking stuff like this. So, this one right here, log base e is natural log. And so if you're doing log base e of e, it is the exponent you raise e to get e, which is 1, right? It's just like when you do log base 2 of 2. That equals log base 3 of 3, which equals log base pi of pi, which is literally right down there. And all those just equal 1, right? Because all of those, there's a little 1 right there in the exponent, and the log equals the exponent that you raise the base to get the thing in here. So it literally just cancels off, right? In each case, here too, and also down here. And you'll just get that 1, right? So that's how the first one with natural log of e is just a 1 right there. And actually also log of 10 is 1, right? Because that's just a common log. It's log base 10 of 10. And so this is literally 1 minus 1 squared, which is 0. All right. So this one, a little hard to see, but there is actually a 0.1 in there, so that's 1/10, okay? So what we should be able to do, if we're going to simplify this without a calculator, is write this thing with a 1/10, okay? So we know that 1/10 is just 10 to the negative 1. So then 1 over 10 squared, right, should be, I want to say 1 over 10 to the negative 2. That's what I want. Is then going to be the 100, right? Because we want to square the 10 to get to 100, and we want to flip it. That's what the negative does. So I can go ahead and write this thing as log base a 10th, right? And then I'm going to have a 10th in there to the negative 2, and then all of that to the 1/3 because of the cube root, right? And then we just do properties of exponents. We just multiply negative 2 and 1/3, so we get negative 2/3. And so log equals the exponent, which is the negative 2/3. And so that is my final answer for that one. So no calculators needed. You can just kind of, in a sense, cancel these. And then this thing is what the log will equal. Same kind of thing up here. Try to always, just with these problems, write the thing inside, the 81 in this case, as the base to something. So 81 is 3 to the 4th. So you can write 3 to the 4th squared. And then just like the last one, we'll multiply those. So we have 3 to the 8th, right? So my answer on that one would be 8. We actually did part of this problem already. Last one, we know that's a 1. And then this is another really important property of logs. Anytime you plug in 1, right, you get 0. That's why when we graphed this one, right, this log, we started at 1, 0. Right? You plug in 1, you get 0. And it's really just because anything to 0 is 1, and it's the inverse function to an exponential. So if you plug in 1, you should get 0. So yeah, that thing right there is literally equal to 1 plus 0, which is 1. And that's it. There's one more kind of concept that we haven't reviewed yet, and that is solving log and exponential problems. So both of these are, I would say, definitely on the harder side for like log equations, inequalities, and exponential equations, inequalities. Both you should definitely be able to solve without a calculator, okay? I would highly suggest you try them first and then pause the video and then, watch me go through it, but don't have to. So hopefully you did pause it and tried them out. If not, I'm going to get into it right now. So this first one, I don't like the fraction, so I'm going to get rid of the fraction. So I'm going to multiply by 3 to the x, okay? So I'll have, over here I'll have 3 to the x squared, and then minus 3 to the x equals 72, right? So then what I'm going to actually do is I'm going to move this all to one side. So I have 3 to the x squared minus 3 to the x minus 72. And what I want you to see here is this has perfect structure for substitution, right? You have a quadratic, right? 3 to the x squared, then you have a 3 to the x, right? So you have this squaring of terms going on, and you have 3 terms. So anytime you see that in math, you can always do this trick where you can always be like, all right, let u equal 3 to the x, and then u squared is going to be equal to 3 to the x squared, right? And so I'm going to change my problem to now be u squared minus u minus 72. And solve it out from there. So this thing actually factors nice. This is u minus 9. This is, u plus 8. And then u is equal to 9. U is equal to negative 8. All right. And then you just have to unsubstitute. So u was 3 to the x. So 3 to the x is equal to 9. 3 to the x was equal to negative 8. All right. This one's actually nice over here because you can't have an exponential equal a negative, right? It's, one of the nice things with exponentials is that they don't equal negative. So if you get that, you can just ignore that. There's no solution there. This definitely works though, right? If you square 3, right, you get 9. So x is 2, and that must work, okay? Don't need to bother checking it because exponentials are well defined. No x's will give you some sort of weird thing over here. This is a different issue, right? This is just related to the range, and the range of exponentials is restricted, which is why the domain for logs is restricted, because the outputs here become the inputs here, okay? So maybe speaking of on the log, let's just do the domain of this thing first, okay? So I want the inside of that log, right, to always just be greater than 0. And so I'm going to move everything to one side, or to the right side, so it's positive x squared. So you've got a quadratic, right, that is shifted down 7, like this. It's not upside down. That's like why I moved it over. So it's right side up. The other stuff I said was good though. It's definitely shifted down, right? So it looks like that. And that thing is less than 0, right? Right in here. And this root would be negative root 7, and this root would be root 7, right? So the domain for this log is anything between negative root 7 and root 7. Anything in there should work, okay? You can actually see it. This picture is going to be the solution to this. And these boundary lines are actually my domain. That's like where the graph shows up, okay? In terms of solving it, so I would multiply by 3, right? Get negative 3. And then add 4, you're going to get 1, right? So just kind of simplifying first, I'm going to be able to move some of those numbers around and get this to be less than or equal to 1, okay? Then I would just use inverse operations. So 10 to the x cancels log base 10 there. And so then you've got 7 minus x squared being less than or equal to 10. Okay. Let's just move everything to the right side again. So x squared, if you minus 7 over, right, is going to be plus 3. And this quadratic, okay, is going to look something like that, shifted up 3. And we wanted to know when is it greater than 0. And it's always greater than 0, right? It's always above that line. So what that means is any number in the world would actually solve this inequality, right? But the log is only defined for certain numbers. It's only defined here between those two numbers. So you can see it because in this picture, this is -1. You can see that the log graph, which is this thing, is always below the dotted negative y equals -1 line. So you can see that anything in there works. It's just where does it even define? And it just doesn't exist over here. So we wouldn't say all reals because like -3 wouldn't work, right? But anything in here would work, right? And so that is my answer. So anything in here is a place where the log is defined and happens to also be a solution to the log.